3.2, least squares regression. So an aggression line, not aggression line, a regression line, that's a line that describes how response variable y changes as an explanatory variable x changes. So here's just an example of a regression line. And you can make these in your calculator. We haven't done them yet, but this is what it would look like. So here's a explanatory variable, the miles driven, and then the response variable is how much the vehicle's worth. So the regression line is like the best fit line that goes between those points. We often use a regression line to predict the value of y for a given value of x. So if you tell me how many miles the vehicle's been driven, I can make a prediction for you as to how much it'll be worth. Okay, so how do you interpret these things? This is what's important for the AP exam. So it's a model, much like density curves from Chapter 2. Those were models for a distribution for like a dot plot. So regression lines are models for scatter plots. The equation gives us a compact mathematical description of what this tells us about the relationship between the two variables. Okay, so scrolling down here, here's the formal definition for a regression line. So it relates y to x, and it looks very much like any other equation of a line, except now you've got this little thing called y hat. So y hat equals a plus bx. So let's identify what these things mean. First of all, that is read as y hat, and that's the predicted response variable for y. So you probably have never seen this notation before, but we predict the outcomes. That's y hat. It's not just y, it's got a little hat on it now. That stands for prediction. Okay. B is the slope. You should be able to identify with that pretty easy. The coefficient on the x, that's the slope. That's the amount by which the predicted variable changes by. So amount we're predicted to change by when x increases by 1 unit. So if the slope is 5, every time x goes up by 1 unit, the output goes up by 5. A, that's the y-intercept. Again, that one's pretty straightforward. So we have y hat, our predicted outcome, equals the y-intercept plus the slope times the inputs. Those are the x values. Okay, so why do we have a y hat now? What's the difference between y and y hat? Well, if we had y, that would be all the values in the entire population if we made a regression line from just using y. So y is like this utopian perfect variable. That's like the population parameter. And there's no way we're going to be able to know that. We're going to try to estimate it. So y hat, that's what we use from our sample. Say we have 10 observations. That's what we get from our sample data. So y hat, that's our predicted values based on our sample. So that's our sample statistic. So we talked about that a little bit last chapter. Y, that's the perfect ideal world. That's the population parameter. We don't have all the values for everyone in the population, but whatever our sample is, we can make predictions. We're going to use y hat. So that's our sample statistic. Okay, so how does this formula look? This guy right here, how does this look on the AP exam? It looks similar, but just so you know the difference when you see it on the formula sheet. So let me just scroll down here. So on the AP exam, it looks like this. Y hat equals B sub 0, little subscript 0 there, plus B subscript 1 times x. So same exact setup, it just has a little different variables, but they mean the exact same thing. The B sub 0 by itself over here, that's the y-intercept. And then the B sub 1, the coefficient on x, that's the slope. So that's just how they were out in the AP exam. It means the exact same thing. They choose different variables for the y-intercept and the slope. So how do you interpret, this is the big idea for us, what's going to be important for us to do in AP Stats. How do you interpret the slope and the y-intercept for a regression line? Well, for the slope, I'll do that in black. So that's the predicted rate of change for y hat. Predicted rate of change for y hat. That's the slope. And the y-intercept in red here. So the y-intercept only occurs, if you look at the graph of a line, the y-intercept only occurs when the x value is 0. So that's our estimate of y hat when x equals 0. Okay, let's look at the first example here. So I'm not going to make you make these yet. So I've already given these to you. I've got the data here. I've already got the line through it. This one has to do with tapping on a soda can before you open it in hopes that it doesn't explode and spray soda everywhere. So these kids shook up a bunch of soda, and they want to see how long you tap on it if it explodes less and less every time. So if they tap on it for 12 seconds, let's say, then a lot of the soda stays in the can and it doesn't explode. Okay, so interpret the slope and y-intercept of the line. So the line's already given to you. It's here. In fact, there should be a little, let's draw a little hat on soda here. So the predicted amount of soda left in the can is 248.6 plus 2.63 times the tapping time. So basically the more you tap it, hopefully the less carbonation explodes out of this thing. So there's more left. So the slope, which is 2.63, what does that mean for us? So the slope of 2.63, what does that tell us? Okay, so remember, slope is rise over run. So you go up 2.63 over 1. So over 1 second, up 2.63. So for every 1 second, 1 second more you tap on this can, there's 2.63 milliliters more left in the can. Or you could say that the amount of soda remaining, because it didn't explode, is predicted to increase by 2.63. And I underline predicted because that's just like an average estimation based on all these points. So that's where this 2.63 came from. So it's predicted to increase by 2.63 milliliters for each additional second that you tap on the can, because slope, this would be like 2.63 over 1. So for each additional 1 second that the can is tapped. So every time we interpret slope in this chapter, it's going to be very similar to this. I'm going to use context, like the amount of soda, context from the problem. I'm going to make sure and say it's predicted to, or on average, or it's expected to. I'm not going to say it's for sure going to do this, but on average, it's going to increase by whatever the slope was for each additional 1 unit. And again, I use context from the problem. Every single problem is very similar to this when we interpret the slope. Okay, how about the y-intercept? So in red here, the y-intercept, which is the 248.6. So that'd be right here graphically. So notice that only occurs when x is 0, so that's what we need to say. So if you tap the can for 0 seconds, we expect it to explode, and there's only 248.6 milliliters left in the can. So 248.6 milliliters is the predicted amount of soda in the can if you don't tap it at all. So if it's not tapped at all. And that's because, let's not forget, the y-intercept, that's always at 0, y. So the x is always 0, and then whatever the y is, like 248.6. So when the x is 0, that's what we predict the y to be. And in slope, we already talked about that. Remember, that was rise over run. So this is 2.63 over 1. So for every increase of 1 unit in x, the y goes up by 2.63. That's really all we're saying, and then we're just putting context to it. Alright, so I'm just going to scroll down a bit here. Part B says predict the amount remaining for a can that's been tapped for 10 seconds. So this is actually a pretty simple question. we have the equation up here for soda. So we make our predictions based on this equation. So if it's been tapped for 10 seconds, all we do is plug 10 in for the x. And we'll make a prediction on how much soda is left. So instead of using x and y's, because if you use x and y's, you have to define what the variable is. You have to write out and explain which is x, which is y. Let's write the equation like this. So make sure you show your work to get full credit for this. But all you have to do is write soda with a little hat on it. So the predicted amount of soda equals, what's the rest of the equation? 248.6 plus 2.63, and then all you'd have to do is plug in 10, because that was the tapping time. We plug in 10 seconds. So predicted amount of soda equals this, which actually is just 274.9 milliliters. So show your work, and then instead of like writing x and y, just use like soda with a hat on it. And then you don't have to define your variables or talk about your variables at all. So let's answer this in context. What did we just find? What is this 274.9 representing? That's the predicted amount of soda left if you tap the can for 10 seconds. So we predict, and notice I underline and emphasize that again. We predict that this much soda is left in a can that has been tapped for 10 seconds. So I answered that in context. I have the right, I think I did the right work, I got the right answer. And I also stress, like, we predicted it, or you could have said we expect this much, or on average it'll be this much. So make sure that part is there. Okay, then let's go to part C. Let's scroll down a little bit. It says predict the amount remaining for a can that has been tapped for 60 seconds. And then how confident are you in this prediction? So same idea. Let's just plug in 60. So predicted amount of soda, and then plug in 60 for the tapping time. Then that's a pretty simple calculation. Just make sure you show your work. And we're looking at 406.4 milliliters. Okay, but here's the issue with that. If you know anything about soda, or how much soda is in a can, we got 406.4 milliliters. That's not reasonable at all. For example, there's only 335 milliliters in a can. So our model, our linear model, doesn't apply out to like 60 seconds. That's not applicable. Well, why is that? Well, we only had data from like 2 to 12 seconds. Just because you tap for 60 seconds doesn't mean there's going to be 400 milliliters of soda left in there. So that's the point. So this is not reasonable. Well, not only does it give you more ounces or milliliters than are in a can, but the bigger issue is we don't have data beyond 0 to 12 seconds. So we only have data for 0 to 12 seconds. So we can't be sure that our pattern, can't be sure that the same pattern continues out past that to like 60 seconds. So maybe 13 or 14 seconds I could give you a reasonable prediction. That'd be okay. But not to 60 seconds. That's a bad practice. That's actually called extrapolation. And we'll get to that definition. That's our last definition for the notes. Okay, example 1 again, aka example 2. How much is that truck worth? So if you know anything about buying cars, the more miles you drive it, usually the less it's worth. So this problem looks at F-150s, has a sample of, 20 of them or something. All these red dots, those are F-150s. Okay, and you don't have to do this in your calculator, but you could if I gave you all the trucks. Here's the regression line. And again, interpret the slope and y-intercept. Okay, so on the x-axis, that's miles driven. That's the explanatory variable. On the y-axis, that's price. So in general, the more you drive it, the less it's worth. That's exactly what the slope is talking about. It's a rise over run. The price over the miles. So for the slope, so that's negative 0.1629. That just means that the price of the truck decreases. So we predict it to fall by 0.1629. And what unit is that? That is in dollars. We predict it to fall by $0.1629 for every mile driven, for each additional mile driven. So again, slope's really simple. For each 1 unit increase in X, we predict a decrease of this in Y. So the price of the truck is predicted to fall by this much for each additional mile driven. That's what that slope means. And for the y-intercept, well, that's for a truck with 0 miles. So that's 0, 38,000. So that's like for a brand new truck. The y-intercept, 38,257. That's our expected price of a truck that's not been driven at all. So it has 0 miles on it. It's a brand new truck. And again, I say it's our expected price or our predicted price. It could definitely be a little different depending on what kind of truck you own. Okay, so that was actually the same approach as we took in the first one. We've done 2 examples now of interpreting slope and y-intercept. Okay, let's do part B. Let me scroll down here. Predict the price of a Ford F-150 Super Crew 4x4 that's been driven 100,000 miles. So we're going to use that regression equation. And I'm not going to use X and Y because I don't want to sit here and waste time explaining or having to write out like Y hat is this, X is this. Again, I'm just going to use the names of the variables in my equation. So I'm just going to write the price with a hat on it. So predicted price is equal to, so that was Y hat, now it's like price hat. And I'm just going to write the equation out. And then for X, the miles driven, I'm just going to plug in 100,000. So if you use X and Y here, you would have to explain on the side where Y hat is the predicted price and X is the miles driven. But I prefer to just use words instead of the variables here. And that works. Okay, so this calculation isn't too bad. 21,967. So we showed the equation, we got the answer, now we just need to answer it in context. So this would actually be the price, or the expected price, for a truck that's been driven 100,000 miles. So that's all we have to finish with. So we would expect, or we would predict, the price of a truck driven 100,000 miles, or 100K miles, to be 21,967. Okay, would you use that same model to predict the price of a truck that's been driven 250,000 miles, 250,000 miles? Explain. And I'm going to say no. I think that's bad statistics. Let's go back to the chart here. So here are all our trucks. We have one that's relatively new, between 0 and 20,000 miles, and then the highest one we have is maybe 140 something, 150,000 miles. So this is all the data that we have. And now it's asking, should we go ahead and predict one that's got 250,000 miles on it? That's not appropriate at all. For one, look at the line. It's probably going to be negative by the time it gets to 250,000. In fact, it is. And we don't have any data regarding trucks with 250,000 miles on it, 250,000 miles on it. So that would be no, that's not reasonable to do. So no, that's not reasonable. 250K is far outside our sample observations. And it actually gives a negative answer. That's not reasonable at all. So again, this would be extrapolation. This would be a bad thing. Like you're making guesses about values that are way outside a reasonable range or the type of values that you have already. Okay, so that's actually the last little bit here is extrapolation. So extrapolation is when you use a regression line to make predictions that are far outside the values you have for X. And they're often not accurate. So this is a bad thing. You don't want to extrapolate. You don't want to make guesses that are way outside your range of values. So in general, don't make values or don't make predictions for x that are either much larger or much smaller than those that are actually appearing in your data. So why is it dangerous? And actually, we kind of observed this in the two examples already. Why is it dangerous? Because it gives you stuff that's unreasonable. So there's no guarantee that the linear pattern that we use, like we're using this line to make predictions, there's no guarantee that that linear pattern is going to continue beyond the stuff that we see, so beyond the given data that we already have. For example, for the trucks, there's no way that linear pattern would have continued and given you a negative answer for 250,000 miles. In the last little bit here, the AP exam common errors. So a lot of people lose credit on the AP exam for not stating that the slope is the predicted rate of change. So they don't say it's like the predicted or the expected or the average rate of change for each 1 unit increase in the x. So don't make that mistake. And then the last couple pointers here. Let me scroll down. When writing the equation, don't forget to use the hat on the y. These are predicted y's. That's what our regression equation does. And you must make sure you know the difference between the actual values for y and the predicted values for y. That's why we use the y hat. And then don't forget, I've already pointed this out, but on the AP exam formula sheet, b sub 1, that's the slope, and b sub 0, that's the y-intercept. And you also get that formula sheet on our exams as well. All right, that's all for these notes. I'll see you in class.